Hey guys, Dio here, and welcome to another video where I share you something in this most unscripted and then explain what I meant in script afterwards. So, as you can see right now, we have this parabola in your regular Cartesian coordinate, and then on the left we have this g equals 0 here, which is a slider, and on the next part I will refer to g as theta, because what g does is that this will rotate this parabola counterclockwise with respect to the origin. And hey, what if we do that now? What if we slide g and see this so-called rotation happen in the parabola? Let's do it. So let me slide this a little bit. Here we go. So like I said, counterclockwise motion. And as you can see here, parabola right now it's gonna be a sleeping parabola. It's gonna sleep, and then I don't know, I guess you can call it wake up. It will wake up again and then becomes a negative parabola, and then I don't know, goes back to sleep in this part, and then boom. What a story. Okay, so we can rotate this parabola using the slider, yeah, but so what? So what that we can rotate this thing? So what that we can make this spin like ultra speed? So what? Here's the next question. What if we can take the derivative, specifically the dy dx of this parabola here? So before I show you what the derivative looks like, let's make some assumptions for a bit. So as you can see here, as I zoom in, this parabola here has a horizontal slope of 0. So I assume at this point that this derivative is going to reach 0 because it's in a horizontal slope. And then alternatively, in this part of the parabola, we have a sort of a vertical slope. So I assume that the derivative is going to be undefined at that point, or maybe there's going to be a horizontal asymptote, like this, just touching this parabola here. And you know what? Let's confirm those assumptions and enable this derivative parameter. So here we go. So like I said, there's a 0 here, there's a vertical slope, and then there's a vertical slope here, and there's sort of an asymptote running along this derivative. And hey, this is just the derivative of the parabola and this rotation. What if we can keep this parabola rotating and see how the derivative behaves? So let me put it in the start position. So here you go. Let me play this. Okay, so here we have this parabola as it rotates. We can see that the horizontal, like the point where it becomes horizontal, is like it's changing differently in each rotation, as well as the what's considered the vertical slope of the parabola. And you may not see this, but you can assume by the way that the asymptote changes and the 0 of this derivative changes along. And hey, you know what? We can confirm that this can be a derivative because, when it's standing, when it's 0 degrees, it's just a irregular 2x. And then when it's like, negative like this, it's going to be like negative 2x. But hey, you've seen the derivative and the rotation of a parabola. What if we could do that to a sine curve? So let me do some setting up real quick. Let me do the sine curve. Okay, so here we have a sine curve and its derivative, which is cosine. As you can see here, the point 0, 0 in the sine curve is has a slope of 1, or it's diagonal, so the cosine here has a y value of 1. And hey, let's do the rotation in this guy and see how the derivative behaves. Let me play this G real quick. And yep. And as you can see, it's gonna be a trippy. Yep. Yeah. Everything's gonna go 90 degrees. It goes ham. All right. So I'll just finish this rotation and I'll go ahead and explain some stuff. And here we go. Okay, that's that. As you can see here, when there's a vertical slope on the sine curve, then there's going to be an undefined part of the derivative. And then when there's a 0 part, then the derivative is 0, like I said. And that's all well and good. But in the next part of this video, I'll proceed to explain to you how to first rotate your curve in math terms, and then using those math terms, I will explain to you how to take the derivative of that rotated curve. So I'll pass the mic to my scripted self. So yeah, I'll see you in a bit. By that I mean the outro. So how do we get the dy dx of a rotated curve anyways? And how do you even rotate a function to begin with? Let's focus on that first. How does one spin a mathematically defined segment of apparent curvature? Okay, let's imagine a point in space which is at some coordinate like xo, yo. With this given point, we then take it to make it rotate around. How much around? Theta degrees around. This theta details the spin distance, or spin stance you could call it. Spin stance of the point xo, yo with respect to the origin. Then after that, we mathematically relate xo, yo together with theta to the rotated coordinate. Doing so requires some old school handling with geometry, trigonometry, and some visualization. And speaking of visuals, we first draw a line segment from the origin to xo, yo, where this line segment acts as a hypotenuse of a right triangle whose legs are simply xo and yo. Then this triangle undergoes the same rotation like before, which puts the triangle legs of xo and yo at a slant. Each of these diagonal legs are then treated as a smaller hypotenuse of a triangle whose legs are horizontal and vertical. Forming a subtriangle of those rotated legs makes a clearer distinction of the rotated point's location because all the smaller legs are horizontal or vertical, whose lengths can be expressed as a relation of xo, yo, and theta. So first let's begin with the lower right triangle. Here you may notice that the triangle has an angle that is simply theta, and that the hypotenuse is simply xo. With those given values, we use trigonometry to identify the length of the triangle's leg, where the opposite side of xo is just xo sine theta, and the adjacent side of xo is just xo cosine theta. Similar to the other triangle, it is apparent that this hypotenuse is simply yo, but what is not apparent is that this tip angle is actually theta, because this small triangle is geometrically the lower triangle, but small and rotated 90 degrees. Therefore, we then derive the other leg's measurements with trigonometry, where the lower side, which is opposite the angle, is measured yo sine theta, and the left side, which is adjacent, is measured yo cosine theta. With the length of the subtriangle's components defined, we can visually infer about the measurement of the x and y of the rotated point. For the x component, the measurement is equivalent if the horizontal length xo cosine theta is subtracted with the other horizontal length, which is yo sine theta. Similarly, the y component's measurement is equivalent if the vertical length of xo sine theta is added with the other vertical length of yo cosine theta. Finally, we have evaluated the x and y of the rotated point, which is defined through these two expressions, where this pair of maths should work for any point in space. Let's take this a step further, shall we? Rather than applying rotation to a point, what about a curve? That's right. And we are going to do that through a type of curve called a parameter. Parametric curves are defined by their x and y component, making it a perfect example for the pair of expressions that we have. And speaking of parameters, how about we first convert our pair of expressions into one so I don't have to distinguish between the two. This parameter is expressed as xo cosine theta minus yo sine theta, xo sine theta plus yo cosine theta. Going back to the curve, any parametric curve is defined by the functions of xt and yt, which are shoved in a coordinate. And like I said, the rotation expressions, which are now a parameter, work for any point in space, which implies that it should also work on curves. If we want to rotate any sort of curve, we simply replace the xo and yo with xt and yt. You know what? I don't think I've written a joke in this script so far. So here's the deal, right? What I'm gonna do is spin, make my parametric curves rotate continuously, and then admire the angular velocity. This is the part where we go back to the main question. What is the dy dx of a rotated curve, or the instantaneous rise over run of a rotated curve? To begin with, you have seen in the first part that there can exist two y values from a rotated parameter, meaning the derivative should not be a function, that should be a parameter, in order to hold that property. Other than that, you may recall about the nature of the derivative, about how it works, that for a certain x value in a parameter, the y value of the derivative is the slope of the parameter at that point. From that, we infer that the domain of the parameter must be preserved in the derivative in order to calculate a rise or a run value of a given abscissa value. Therefore, in the rotation set, the x component of the derivative parameter remains the same, which is xt cosine theta minus yt sine theta. Now for the next missing piece of the puzzle, the y component. This is a component representing the dy dx of the rotated curve, or in other words, the rate of change in y as x changes. So how do we do that? Well, I've hinted at the answer already. If you've watched the second episode of my PPF series, you may recall that the dy dx of any parameter is just dy dt over dx dt, which is the derivative of the y component over the derivative of the x component. Simply put, we differentiate both xt cosine theta minus yt sine theta and xt sine theta plus yt cosine theta. Then arrange them on a fraction for the y component. Differentiating, of course, must be with respect to t because theta is not the variable that experiences the rate of change, so theta is treated as a constant here. This video, however, is not a place where we dedicate 10 minutes to algebra, so real quick, the derivative of the rotated parameter is written as y prime t cosine theta plus x prime t sine theta all over x prime t cosine theta minus y prime t sine theta, where x prime t is the derivative of xt and y prime t is the derivative of yt. This entire thing should be the y component of the derivative parameter, which completes the entire thing. Thus, we have the dy dx of the rotated parameter. And basically that's it for this video. I'm not gonna ask you to like or subscribe or anything. Maybe I just want you guys to like share this to a friend or someone you know who is interested in this topic. But hey, let's do some behind the scenes real quick. So there are many things you can do with this, with the parameter that I've derived. And in these folders is where everything happens, if you haven't guessed that. So hey, here's xt and this is yt. And then, you know, we have sine t here, which is, you know, the thing that's rotating right now. So, hey, instead of just functions that you are rotating, you could also do that to other parametric curves, such as, let's see if I remember this right. So, if xt is t cubed minus t, and yt is like t squared minus 1, you will get a right strophoid. And here, you know, you can see the strophoid, it rotates, and at the same time you can see the derivative of that rotated strophoid, which is very cool. And yeah, this is one of common parameters that are double y valued and all that good stuff. And hey, you know what, since you've made it this far, let me show you something that maybe in the last episode you may recognize. So let me write it down. So it's like 2 plus sine t cosine t for x of t, and then 2 plus 4 sine t times sine t. There we go. Yep, this is it. We have graphed Amogus unscripted. And if you haven't seen it, this is the parameter. Is when xt is this and yt is that. And you can make the Amogus spin maybe faster, make the crewmate spin and take its derivative. Please don't quote me on that, but of course I haven't mentioned here's a derivative and here's the rotated part, and of course the g is theta in the scripted part. And yeah, that's that. And you can you can have fun with this. I will send the link of this Desmos under the description, and you can come up with some parametric curves and see their rotation and their derivatives. Actually, this is a bit too dynamic. Okay, this is good enough. So yeah, again, thank you so much for watching, and I hope you have a good day, and keep on sussing, math folks. I don't know why I'm ending with that, but yeah, I'll see you guys in maybe the next video.